Yeah, so this is the day where we take you through translation. Okay, we did transcription, which is not super complicated. In fact, it's a lot like DNA replication, except you're only matching one strand of RNA to the DNA. There's only one enzyme doing it, the RNA polymerase. We wind up with this mRNA transcript that we then take through editing, which we talked about yesterday. Editing is where you take out the kind of nonsense junk RNA and splice the rest back together. And you get this thing that when then we cheated. We jumped ahead and figured out the code, which was this thing. Y'all have your own secret decoder wheels now. And before we get into what actually happens as that code gets unlocked, one of the really cool things here is that code right there, I don't want to oversell this, like I said, but like if you are from North America or Asia or Africa or South America, or if you are a tree, or if you're a beetle, or if you are a bacterium, even if you're a virus, that code right there is the same and works the same. Like AUG codes for methionine, does not matter where or who you are. All of that works the same. Like this is the secret to how life codes for life.
How did we find this?
A lot of work, a lot of different people building on each other's work. And at this point, not only do we know that that's how the code works, but we know what our version of the code is almost completely. And we know a lot of the genes and proteins that are involved. So yeah, we're on our way to really, really understanding how all of this works.
Is it that symbol in a human body, or is it a little bit more?
Well,
is that still the only 20 extra?
there's only 20 amino acids that make up the proteins that make you up. There's only 4 bases in RNA. There's only 4 bases in DNA. But if that sounds simple, understand that an entire computer that's well beyond your or my understanding is based on only 2 things, zeros and ones, right? So like 4 bases and 20 different amino acids is a lot. You can make really complicated stuff with that. Anyway, let's look at how this actually happens. First of all, here's why proteins are so cool. A protein is a chain of amino acids, just like DNA is a chain of nucleotides. You knew that. And which amino acids there are in what order make proteins fold up in particular ways. When proteins fold up in particular ways, they take a characteristic shape. And a protein's shape is very much what makes it do the things it does. A protein's shape, if we're talking about receptor proteins, it's that shape that lets something plug into it to make you smell roses or to make sugar enter your cells if it's insulin. The shape of collagen in your face, which lets collagen hold on to other collagen like a mesh net, is what keeps your face from splitting in 2 when you do this ridiculous thing I made you do online. It's all about the shape. So sometimes it's hard to get that connection between DNA and protein. But if you think about DNA 3-letter codes going to mRNA and tRNA and then amino acids, coding for particular amino acids. If the DNA is determining which amino acids there are, and the amino acids determine what shape the thing is, then the DNA is determining what shape it is. So that's where this is going. Okay, here comes the drawing part. Hold up a second. Here's what's gonna happen. Were you not done? So when I get something like this, there's gonna be moving parts. Like for example, that's gonna come in, that's gonna come in. Wait till you see all the moving parts before you draw. I'll give you another couple minutes to finish this. All right, here we go. First thing that happens when the edited mRNA squirts out of the nuclear pore into the cytoplasm is the ribosome finds it. The ribosome is built of two parts, looks like a hamburger, creatively named the small ribosomal subunits and the large ribosomal subunit. Those things clamp on. When you draw this, please be precise about how many bases the hamburger covers. The hamburger should be clamped down on exactly 6 bases. That's by design. The ribosome, by the way, is the one thing we didn't have in our paper shapes. So if you're like, well, where was this on the paper shapes? We didn't have a ribosome. Isn't what scary looking? I don't know.
Like super complicated.
I mean, I simplified it, obviously. But yeah, it is actually a big wad of ribosomal RNA. Oh no, yesterday I did. So think of this as like almost like a tape that feeds through the machine, and the ribosome is the machine. And of course, this is much longer than 9 bases in real life. We're talking about, hundreds or thousands of bases long. And this tape's going to basically feed through the ribosome 6 bases at a time. Well, I guess technically 3 bases at a time. Because remember, it's 3 bases at a time is how that code gets read. All these codons, we know the code. You're about to see physically what's going on as the code gets decoded, translated. So we now have 2 of the 3 kinds of RNA. We've got mRNA here, and then the ribosomes are made of rRNA. We're about to see what tRNA does, although you already kind of know. You remember those big pieces of the paper shapes. We had our tRNA go and pick up the amino acids, slot them into them, and then bring them to the mRNA. That's what's about to happen. Okay, here we go. I'll come back to anything that you need me to come back to. Step 2, this little jumbled up strand of RNA is a tRNA molecule. Don't draw or write yet, just watch. Watch, watch, watch. That tRNA, as all tRNAs do, has kind of 2 business ends. It's got 3 bases sticking out one end. In this case, the 3 bases are uracil, adenine, cytosine. And on the other end, it has a little hook that's really good at grabbing one particular amino acid. Now, the tRNA that has UAC on the end there always picks up methionine. And then what's going to happen is that in step 3, the codon on the messenger RNA is going to attract the tRNA because UAC is complementary to AUG. Just like you took, the sizes are different here, but remember that big glob paper shape that had 3 bases on it, and you plugged it into your mRNA, and it was dragging the amino acid with it. That's what's going on here. Okay, so that's what you draw now, and that's about halfway. Pretty.
So the thing that has the UAC on it.
Yep.
Why does it look like that?
Because it is so all of these things, the ribosome, the tRNA, and the mRNA are all made out of the same stuff. which technically is just a big long thread of repeating nucleotides like one chain of that, right? But the tRNA is such that it folds up in a way, kind of like proteins do. Like all of this is actually letters. We just only pay attention to the 3 letters that stick out the butt of the thing, right? That's called the anticodon. Okay, this right here is the anticodon. And we call it that because it's complementary to the codon, which is this. Keep in mind that that codon's only there because of DNA that was TAC, right? So the DNA that said TAC coded for mRNA that said CUG, which then matched the tRNA that was UAC, which determined that it was methionine. Like, there's a lot of steps here, but it was the DNA that coded that amino acid, which is why we say DNA codes for protein. So you can see now the step that we skipped. Yesterday on the cow insulin worksheet, I gave you this, right? A big long thing of mRNA, and you skipped straight to this. Well, there's a step in between that, right? There's tRNA that matches up and actually brings the amino acid. Any other questions? What I think I'll end up doing is actually posting online this sequence of slides with animations intact so that you can do it yourself and kind of replay this for yourself. And again, I'll go back to anything you missed. But so then it's kind of more of the same for a while, where the next, by the way, what's the next tRNA going to be? Caleb? GAG comes in. Turns out GAG always carries leucine. So you can see how the amino acids come in now. All that's left is, well, how do those amino acids attach to each other? There is a particular kind of bond, a kind of chemical covalent bond that attaches amino acids together. Stop drawing for just a second. Let me just show you this process real quick. So here we've got our 2 amino acids attached to our tRNA. Watch up here. What happens is the methionine is going to get stuck onto the end of the leucine. And the first tRNA is just going to fall off. That's our second to last drawing. Only one more. Can you tell what's coming next? Benny, what's coming next? Where do we need to go? We've done AUG and CUC. We got to get to AAG. And so what's about to happen is that string of mRNA is going to slide down 3 bases so that the AAG is in that second slot on the ribosome. Okay. Ready? Understand that this like pushed my PowerPoint skills to the limit, making something animated like this. But here's how it goes. Don't draw it yet. Don't draw it yet. The string moves down 3 bases. Up, down 3 bases. In comes the next one, which happens to be carrying, when it makes a sound, lysine. And then the whole mess, you know, the 2 ones we've strung together with the peptide bond, they get stuck onto the end of that one, and the old tRNA falls off. The end. Well, not the end, but like that's the last drawing you have to do. Where do you want it? Do you want it here? Or here? Or here? Probably here, right? Yeah, put it there. There's a little bit more. I'm gonna leave it for tomorrow. Basically, all it says is this happens until you hit a stop codon. Remember the stop codons? UAG, UAA, UGA maybe? Yeah, those are the ones that instead of attracting a tRNA, they attracted basically a pair of scissors that cuts it off. That's how you build a protein. So your homework that I just gave you is a series of versions of the code with one aspect of the code filled in. Like some of them have the DNA and you got to get to the mRNA, tRNA, and amino acids. Some of them give you the mRNA and you got to work backwards and forwards. It's just practice using the code. If I were you, I'm not, but if I was, to help me in these kind of beginning stages of knowing that code, what I would be doing is at the top of my page, I would make myself a little cheat sheet. And my cheat sheet would look something like this. And I would go, okay, if there's an A, this would be a U, this would be an A. I guess you don't need that. This is a T, this is an A, and this is a U, this is a G, C, G. And that would be my little cheat sheet for doing something like that, where I got to go back and forth between all these different complementary bases. Does that make sense? I don't want to tell you how to do your homework, but I think that would be an easy way to do it. Then, of course, when you want to get to amino acids, you got to use the wheel. And you got to look 3 bases at a time. And you got to remember, even though I printed it on there for you, some of you are going to forget. You're going to start putting tRNA into the wheel and get the wrong answers. It doesn't work that way. This wheel is designed for mRNA. It's a way to cheat, a way to skip ahead. So when you find amino acids, you got to make sure you're using the mRNA, not the tRNA. Hazen, you had a question?
I was just wondering if we're going like eventually, if we're going to be able to use the wheel on one.
Oh, for sure. I'll never make you memorize the wheel. When you have to do this on a test, you will be given the wheel. Promise. Okay? And you will have to do this on a test. Cool. That's your homework. It is due tomorrow. Test Friday is tentative. I'm starting to lean towards Monday or Tuesday. Just so you know, I'm not going to rush you into anything. It's important stuff. It's a secret to life, people. Please get out your homework from yesterday, the other secret decoder wheel homework, and I will check that.